Thank you for joining us on Synthesis Workshop. On today's Research Spotlight episode, we're joined by Max Palkowitz. Max got his bachelor's degree in chemistry from Boston College, where he did undergraduate research in the Morking Group, working on stereospecific amination of alkyl boronic esters. He then came to Scripps, where he's currently completing his PhD in the Baran lab. In addition to the work he'll describe today, he was also part of the team that put together a great 2020 accounts of chemical research paper called A Survival Guide for the Electro-curious, which I'd encourage you to check out if you're interested in this research area. The link to the paper can be found in the comments. And with that, I'll let you get started, Max. Thanks a lot for joining us today.
Thank you, Matt, for the kind introduction, and for allowing me the opportunity to share our recent work on this platform. As the title may suggest, this work is largely driven by electrochemistry. But before we get too far into the talk, I think it's valuable to highlight some of the attractive features of electrochemistry as it relates to synthesis. First, if the reduction potential of a specific functional group is known, then the reactivity of the electrochemical cell can be tuned to selectively engage with that functionality. This stands in contrast to chemical reagents which, in principle, operate at fixed potentials or fixed potential windows. With electrochemistry, both highly oxidizing and deeply reducing reactivity paradigms are possible. This was leveraged beautifully by Harran and co-workers' synthesis of diazonamide analogs, where an electrochemically induced macrocyclization was carried out under constant potential electrolysis. Chemical reagents in this system, while giving the desired product, also gave substantial amounts of byproducts arising from competitive oxidative pathways. Second, electrochemistry can confer a heightened degree of safety through mimicry of otherwise highly reactive chemical entities, as exemplified by this work from the Perichon lab, where a 1,2 addition to a carbonyl was achieved through electrolysis of an unreactive alkyl chloride in the presence of a ketone electrophile, thus representing a pyrophoric-free alternative to an organometallic addition. Finally, the low cost and optionality for reactor design allows for facile large-scale applications. One such example is from BASF, where the anodic oxidation of para-terpene in the presence of methanol gives the corresponding acetal, which is used towards the synthesis of lismorale, a common ingredient in many soaps and shampoos. It is worth noting that the phthalic acid dimethyl ester is concomitantly reduced, while para-terpene is oxidized, highlighting the need for both reductive and oxidative half reactions to be balanced in any electrochemical reaction. When looking for an application of these features of electrochemistry, we quickly found one in the synthesis of linear polyenes that could be used in polyolefin cyclizations to access a variety of terpene natural products. While most students of synthesis may be able to trace these complex terpene natural products, such as progesterone, cholesterol, and isosteviol, back to a linear polyene precursor, the assembly of such a substrate is not so straightforward. Classical retrosynthesis logic from Johnson's landmark tool synthesis of progesterone is characteristic of many conventional approaches, where the retrosynthesis is not intuitive, the building blocks do not easily map onto the product, and are typically designed for a single polyene product. Typically, such approaches suffer from a variety of redox fluctuations, functional group interconversions, and protecting groups which significantly lower the ideality of this approach. This stands in contrast to the way that nature synthesizes polyolefin structures. Nature takes a more unified approach by using common building blocks that undergo discrete activation steps to make building blocks that are stitched together in an assembly line-like fashion. Drawing inspiration from nature's approach, we envision that these linear polyenes may be traced back to bifunctional building blocks bearing both sp2 and sp3 cross-coupling handles that easily map onto the target structures. The tactic of choice for this platform was the decarboxylative alkylation reaction that our lab had developed a few years prior, where a TC-NHPI redox-active ester is coupled with an alkenyl zinc reagent employing nickel catalysis to form substituted alkene products. In the initial manifestation of this platform, we were able to access these linear polyenes using this decarboxylative cross-coupling approach. In the forward sense, decarboxylative cross-coupling of this alkyne-bearing redox-active ester with the vinyl zinc reagent generated from the siloxy-bearing vinyl iodide forged the first carbon-carbon bond in 69% yield. Next, deprotection and oxidation of the TVS-protected alcohol unveiled a carboxylic acid, which, upon activation with DIC and TC-NHPI, gave us our next redox-active ester. This redox-active ester was uncoupled with our next alkene fragment in an identical fashion as before in 43% yield. Finally, deprotection and concomitant appel delivered an alkyl bromide, which was directly employed in a nickel-catalyzed cross-coupling with an alpha-iota enone using manganese as a terminal reductant, delivering the target polyene in 34% yield. While this approach used modular building blocks, a reductive radical cross-coupling to forge the final CC bond, amongst many other canonical radical cross-couplings, there were several significant drawbacks that severely hindered the practicality of this approach. First, 4 equivalents of vinyl iodide were required to get synthetically useful yields of cross-coupled products. This, of course, comes at the cost of using 8 equivalents of terpetal lithium to make the corresponding organozinc, which had obvious scalability and safety liabilities. Additionally, the traditional decarboxylative cross-coupling was operationally cumbersome as it required the preparation of an organometallic, titration of that species, and various transfers, rendering reaction setup a multi-hour process. The need for pyrophorics to activate the sp2 coupling partners necessitated a reliance on protecting groups and the need to use isolated redox active esters in the coupling, since the urea byproduct from in situ activation quenches the organometallic reagent. Finally, a large excess of metallic manganese reductant in the final cross-coupling step had its own scalability concerns as it made the reaction highly heterogeneous. In reflection of this initial approach and the many drawbacks, we wondered if the chemoselectivity, safety, and scalability that electrochemistry offers can ameliorate essentially all these synthetic shortcomings. After going through the literature, we were pleased to see that there have been several reports of electrochemically driven sp2-sp3 cross-couplings that could allow us to at least eliminate our use of pyrophorics. Pioneering work from Perichon and coworkers demonstrated that vinyl iodides can be efficiently coupled with alpha haloketones. More recently, Hansen and coworkers showed that unactivated alkyl bromides and aryl bromides could be coupled in a similar fashion. What was most exciting for us was that there are several reports of using NHPI redox active esters and reductive cross-electrophile couplings. Riesman and coworkers demonstrated that coupling with vinyl bromides may even be rendered enantioselective using an organic reductant, TDAE, and a chiral box ligand. More relevant to our intended electrochemical approach, Jameson, Fang, and Bio demonstrated that arylation of redox-active esters with aryl bromides could be achieved in a divided cell. Just a year later, Lauren demonstrated that the same could be achieved in an undivided cell with the sacrificial zinc anode, while also demonstrating that the carboxylate of the carboxylic acids could be directly employed using P2 to achieve in situ formation of the NHPI redox-active ester. These two reports are complementary to Wakes' zinc-mediated cross-electrophile couplings. Inspired by all these precedents, we believe that developing an electrochemical decarboxylative alkylation using the vinyl iodides we had should be feasible. After a brief optimization, we were able to develop conditions for an electrochemical decarboxylative alkylation using nickel chloride hexahydrate, BIPI, tetrabutyl ammonium perfluoroborate as an electrolyte in DMF, a sacrificial magnesium anode, and a reticulated vitreous carbon RBC cathode. We were able to generate cross-coupled products in synthetically useful yields with low equivalents of vinyl iodide coupling partners. Already, this was a significant improvement over the chemical decarboxylative cross-coupling. Upon switching to an electrochemical reactivity platform, we saw an increased functional group tolerance. We can now couple vinyl iodides that bear skip dienes. Under chemical conditions, these vinyl iodides would decompose when lithiated through a lithium-ene reaction. Here, since no such organometallic is being generated, we were able to use them in productive cross-coupling. We also found that free alcohols could now be tolerated, allowing us to potentially limit our need for protecting groups. Additionally, we found that this chemistry was very easy to scale on the benchtop, which would be needed to sustain a synthetic campaign. To further probe the scalability of this reaction, we partnered with Asimchem, and they were able to perform this coupling on a 100-gram scale using recirculating flow. While our first forays into the electrochemical approach ameliorated many of our past limitations, it was not without its shortcomings. For instance, we could not couple acid-bearing vinyl iodides very efficiently. Further, we were unable to translate the coupling to an in situ protocol, further suggesting that our reaction is sensitive to the carboxylic acid moiety. In light of these limitations, we set out to achieve an aspirational goal of being able to successfully tolerate this functionality. Doing so would allow us to pursue a more ideal synthetic sequence where we could selectively activate our acid cross-coupling partner in situ and then couple it with a vinyl iodide that already bears the free carboxylic acid needed for the next coupling. Repeating this process in an iterative fashion would allow one to build polyene motifs without any intermediate concession steps, redox fluctuations, or even protecting groups. After slightly changing our model system, we sought out to re-optimize the reaction to tolerate free carboxylic acids. Unfortunately, we were constantly met with failure in this endeavor. Permutation of electromaterials, ligands, and metals, along with many other parameters, failed to move the needle significantly for this coupling. It wasn't until we started exploring electrolytes that we encountered the breakthrough that we needed. When silver nitrate was added to this reaction, the yield was significantly improved from 18% to 52%. Additionally, when this additive was employed in our in situ protocol, we observed a significant boost in yield. This serendipitous discovery had simultaneously addressed both major limitations of the method in one fell swoop. However, this additive was rather odd. Silver nitrate is usually employed as an oxidant, yet it is having a significant impact on a reductive transformation. So what is going on here? Silver nitrate had affected our reaction in a very different way than the other additives had. First, silver nitrate drastically altered the byproduct profile of this reaction. On the left is the byproduct profile as a function of charge passed, or Faraday per mole. We can see that there is an immediate and fast consumption of the redox active ester and formation of acid and dimer byproducts, while product forms very slowly. If we run the same study with the addition of silver nitrate, we see four major differences. First, the redox active ester is consumed more slowly. Second, product is forming at a steady rate. Third, there is significantly less dimer forming. And finally, there is an induction period in the reaction that is proportional in time to the amount of silver nitrate that is added to the reaction. Nothing happens for the first 0.3 Faradays, or equivalents, of electrons added, which lines up with the 0.3 equivalents of silver we use. During that induction period, we also observe rather unusual color changes. Without silver nitrate, this reaction instantly goes red when electrolysis begins. However, with silver nitrate, for the first 0.3 Faraday per mole, we see a gradual change from a cloudy white suspension to a clear homogeneous green to finally the characteristic red that we attribute to low valent nickel. Finally, we observe that the cathode is covered in a gray film that begins to build up during that first induction period and persists throughout the reaction. All these observations led us to hypothesize that perhaps silver nitrate is first being reduced and plated on our electrode prior to the reaction taking place. To put this logic to the test, we electrolyzed a solution of silver nitrate in DMF at a reaction current of 6 mA for 0.3 Faraday per mole. During that time, a visible deposit formed on the cathode and the solution went colorless. Upon completion of this first phase, we added a solution containing our starting materials, catalyst, and ligand and ran the reaction for the remaining 2 Faraday per mole of charge. Unfortunately, we were unable to replicate the effect that silver nitrate had in the preparative reactions. However, we quickly realized that something was missing in this setup that may be crucial. The electrode preplating with only silver nitrate never generated the white heterogeneous suspension we observed in the preparative reaction. Given silver's high halophilicity, we thought that perhaps silver nitrate and the nickel chloride undergo a rapid salt metathesis to generate silver chloride and nickel nitrate, and it was the presence of that silver and chloride that was important. Putting this logic to the test, we added lithium chloride to the first phase of this preplating procedure, and we were pleased to see the expected reactivity boosts. To rule out the possibility that lithium chloride was simply acting as electrolyte, we tried this procedure with lithium nitrate and did not observe the same boosts. Finally, we had observed empirically that if the silver solution is allowed to sit too long before electrolysis, it will discolor and give poor yields. If we did the same in the preplating procedure, we observed a similar effect. These results led us to believe that silver nitrate is in some way affecting the properties of the cathode. To further test this, we took the coated electrode out of the reaction and used it in a subsequent reaction where no silver was added. We observed the same reactivity boost here. This further suggested that silver nitrate is altering the properties of our cathode. To further study this phenomenon, we teamed up with Professor Scott Anderson and Dr. Paulo Perez at the University of Utah. Paulo and Scott were able to analyze our electrodes with scanning electron microscopy and energy dispersive X-ray spectroscopy to characterize how silver nitrate was affecting this surface. What they found was that in the reactions where only silver nitrate was used in preplating, large faceted crystals of silver were covering the electrode surface. However, in reactions where silver and a supporting halide were present, they observed that the electrode surface was covered in well-defined silver nanoparticles. Finally, in reactions where silver and a supporting halide were present but were allowed to undergo photochemical decomposition, only diffusion-limited aggregates of decomposed silver were present in dendritic growth patterns. Collectively, this led us to hypothesize that it is the silver nanoparticles that form on the electrode surface that are responsible for the reactivity boosts when using silver nitrate as an additive. While there are relatively few reports on how silver nanoparticles can support homogeneous catalysis, there are many reports on how silver nanoparticle functionalized electrodes, prepared in a shockingly similar way to those in our reaction, can be used in the realm of electroanalytical chemistry. Silver nanoparticle electrodes have been used extensively as sensors for various analytes. These modified electrodes operate by altering the kinetics of electron transfer onto analytes of interest. This usually is achieved by a change of overpotential for analyte oxidation or reduction, which results in an amperometric detection. In principle, these modified electrodes alter chemoselectivity of electron transfer, which has underexplored applications in synthetic methodology. A few examples of this technology in play can be seen on the bottom portion of the slide. Peroxide detection, which is usually not observed on graphene oxide electrodes, is suddenly detectable when that surface is coated in silver nanoparticles. Nitrobenzene reduction shifts nearly 250 millivolts more positive, i.e. more fusible, when silver nanoparticles are put on the electrode surface. In a more dramatic example, benzyl chloride's reduction potential is made 500 millivolts more positive on silver nanoparticle-coated glassy carbon electrodes. All these examples, and countless others from the sensor literature, made us wonder if silver is affecting the reduction kinetics of something in our cross-coupling reaction. To further study the electrode kinetics of our reaction, we teamed up with Professor Hector Abrunja and Kara Gannett at Cornell University, where they employed rotating disk electrovoltammetry to gain deeper insights into the electron transfer events of the reaction. The first component of the reaction we analyzed was the BiPi ligated nickel catalyst. On the top left is the voltammogram of nickel chloride BiPi over 5 successive scans on an unmodified glassy carbon disk electrode. Here, we can see that the current response diminished rapidly over successive scans, which is indicative of electrode passivation through absorption. However, on the silver nanoparticle functionalized analytical electrode, we see that we can still retain a current response after several scans. While the passivation is not totally halted with silver, it is significantly slowed down. This suggested that the silver nanoparticle layer is preventing electrode passivation, which occurs through absorption of the catalyst on the electrode surface. Further testing this logic, if the catalyst is cathodically deposited on the electrode surface, then it should be reactivated through an oxidative stripping sequence. Indeed, if we run a plus 1.5 volt constant potential electrolysis on that electrode after we have passivated it, and then continue to run measurements of the nickel BiPi system, we see a restoration of detection of the catalyst, further suggesting electrode passivation as an off-cycle pathway. We also found that there is a potential cutoff for electrode passivation. If the sweep is stopped early at minus 1.6 volts, then we could consistently retain our current response for this system. Past this potential, we begin to see electrode passivation. This led us to wonder what the actual potential of a reaction was. Using a reference electrode, we found that the potential of our cathode is nearly 500 millivolts more positive with silver nitrate operating at an overpotential of just minus 1.1 volts. Without silver, the reaction is running at minus 1.66 volts, which is just above the potential cutoff where we begin to see electrode passivation. Putting all these observations to the test experimentally, we see that these mechanistic insights track with the preparative reaction. Entries 1 and 3 are simply the standard reaction with and without silver. If the catalyst is being pulled out of solution through decomposition on the cathode, then adding more catalyst should improve the yield. Indeed, that is the case in entry 3. If the reaction is sensitive to cathode potential, then running the reaction at the potential at which the reactions with silver is operating should improve the yield. Indeed, if the reaction is run without silver, but at a constant potential of minus 1.15 volts, we see a modest improvement in yield. Finally, if we periodically oxidatively strip the cathode of anything that may have deposited throughout the reaction, then we should improve the yield as we saw in the oxidative cycling experiment. Indeed, if we perform a brief oxidative cycle every 11.5 minutes or 0.2 Faraday per mole, then we see an improvement in yield. While all of these experiments help validate the findings in the RDE experiments, they didn't fully achieve the level of improvement we were seeing with this additive, so there must be other roles that silver is playing. We next moved on to studying the differences of behavior between the catalyst and the redox active ester. Both are species that have very similar reduction potentials and equally capable of being reduced electrochemically. A Levitch study was carried out to study how the diffusion of these species to the electrode surface is affected by the silver nanoparticle functionalization. Without getting too deep into the theory and mathematics of these experiments, the important takeaway is that the slope of these lines are directly proportional to the diffusion coefficient of the analyte. If you look at the Levitch analysis of the catalyst, we see that the slopes of these lines are relatively the same, suggesting little changes to how quickly the catalyst reaches the electrode surface. However, the Levitch analysis of the redox active ester reveals a significant change in the diffusion properties as a function of surface modification with silver nanoparticles. The lower slope observed with the RAE on the silver modified surface suggests that this species' diffusion to the electrode surface is slowed down. Putting this together, we identified another role of silver where it helps to slow diffusion of the redox active ester to the electrode surface where it undergoes background reduction. This explains why we observed the slower rate of consumption of the redox active ester in the byproduct distribution over time study from a few slides ago. While all this helps rationalize the improved yield we see with silver nitrate, it does not explain why it was the acid-bearing vinyl iodides that necessitated this additive in the first place. To study this, we performed RDE voltammetry on the catalyst with either the carboxylic acid-bearing vinyl iodide that was problematic without silver, or its methyl ester analog, which did not present such challenges in the cross-coupling reaction. With the methyl ester vinyl iodide in the catalyst, we see the expected passivation that we observed in our first RDE studies. However, looking at the acid-bearing vinyl iodide in the catalyst, we do not see such passivation. If the catalyst was not decomposing on the electrode, then where was it going? To explore this, we performed RDE of the catalyst and RAE in the presence of either vinyl iodide, and we found that with the acid-bearing vinyl iodide, there was a second reduction event, which was not present with the methyl ester. We hypothesize that this second reduction event is a reduction of a post-oxidative addition, either nickel 2 or 3 complex, to a nickel 1 alkenyl species. These over-reduced low-valent nickel 1 complexes can lead to degradation of the starting material and catalyst deactivation through formation of catalytically inactive nickel 1 dimers, among many other off-cycle pathways. Comparing the onset of these two reduction waves to the cathode potential of the reaction without silver nitrate and with silver nitrate is particularly informative. This finding implied that the silver nanoparticle layer decreases over potential to the point immediately before the second reduction wave, whereas the use of bare glassy carbon electrodes, more reducing potentials beyond the second wave under standard reaction conditions, are applied. Putting all this together, we propose the following reaction mechanism. In the first 0.3 farads per mole of the reaction, silver 1 is reduced to silver 0 and forms silver nanoparticles on the electrode surface. After all the silver is consumed, the nickel cycle begins in accordance with expected radical cross-coupling cycles. Low-valent nickel is generated from the reduction of nickel 2. This low-valent nickel species undergoes reversible oxidative addition to the vinyl halide to form a nickel-alkenyl intermediate. This nickel-alkenyl complex ultimately captures a carbon-centered radical that is generated from the redox-active ester upon SET from another nickel center and subsequent decarboxylation. This nickel 3 intermediate then undergoes reductive elimination to form the desired product, as well as a nickel 1 species that can engage with the RAE to form another carbon-centered radical, as well as a nickel 2 species that can re-enter the catalytic cycle. The silver nanoparticle layer helps support the catalytic cycle through several means. First, it helps slow down catalyst degradation by preventing absorption. Second, it lowers the overpotential below the potential for catalyst decomposition. Third, it slows diffusion of the reductively labile redox-active ester to the electrode surface while not affecting the diffusion properties and ultimate reduction of the catalyst. Finally, in the case of acid-bearing vinyl iodides, it helps to prevent catalyst deactivation through over-reduction of the post-oxidative addition nickel-alkenyl species. So what has all this done for us in our pursuit of linear polyenes? Let's re-examine our old route to the polyolefin substrate for progesterone. Before the application of electrochemical tactics, the synthesis was marred by reliance of pyrophorics, protecting groups, large excessive coupling partners, and intermediate concession steps. After having developed our new electrochemical decarboxylated alkylation, we can simply perform coupling after coupling of these bifunctional halo acids used in slight excess without the need for protecting group chemistry, using in situ RAE synthesis to further streamline the route. Finally, after using the same Appel reaction we used before, we could couple the final alpha halo enone using an electrochemical variant of the previously used reductive coupling. This dramatically reduced our step count from 9 steps in the chemical approach to 6 steps in the electrochemical approach. Here, the silver nanoparticle functionalized electrodes transformed the route into an assembly line-like process with dump and stir chemistry. To further demonstrate the strategic and tactical improvements that this shift in platform methodology granted, we pursued several other linear terpene formal and total syntheses. First, to show that our platform could be used to make other polyenes in an assembly line-like fashion, we targeted Siegel's polyene cyclization substrate used in their synthesis of celastrol. Cutting the sp2-sp3 linkages in this polyene brings us back to these building blocks bearing an electron-rich arene and an aldehyde. In the forward sense, coupling the arene-containing fragment with the bifunctional halo acid gives a coupled product in 48% yield. Subsequent coupling with this aldehyde-bearing vinyl iodide forges the desired tetrasubstituted olefin in a modest 23% yield on gram scale, completing our formal synthesis of celastrol. We next targeted Snyder's radical polyolefin cyclization substrate used in the synthesis of isosteviol. Following a similar retrosynthetic logic leads us to 3 building blocks. In situ activation and coupling of the alkene-bearing acid with the 1,3-diene-bearing vinyl iodide affords the desired product in 53% yield on gram scale. A second coupling with this beta-keto ester-bearing vinyl iodide affords our formal synthesis endpoint in 49% yield on gram scale as well. In an effort to further explore functional group compatibility, we set out to pursue total syntheses of other smaller linear terpenes. Coupling of this epoxide-bearing acid with a furan-bearing vinyl iodide delivered the coupled product in 47% yield, which after epoxide opening with lithium triethyl borohydride gave the natural product Ambliol A in 63% yield. Next, the bisabolene natural products were targeted as an opportunity to test coupling with secondary carboxylic acids. Both alpha and beta bisabolene were made from this common precursor and the corresponding vinyl iodides in good yield to directly afford these natural products. In an effort to test the scalability of the silver nanoparticle-enabled cross-coupling protocol, we targeted EE-homofarnesol, which is an intermediate in the synthesis of ambroxide, a molecule used extensively in the fragrance industry. Coupling this polyene-bearing acid with an alcohol-bearing vinyl iodide gave the product in 59% yield on 30 millimole scale. Just to show you what this looks like in practice, the picture on the left is our benchtop reactor, the ICA Electrocyn, equipped with 6 vials, each containing about 1/6 the total reaction mixture that was prepared as one solution. On the right is our isolated product, of which we isolated roughly 4 grams. Next, we targeted California red scale pheromone as an opportunity to test beta-iodoenoates and esters. First, coupling of this alkene-bearing acid with a beta-iodoenoate gave the substituted enone in 54% yield. A 1,4 addition with an organocuprate, followed by saponification, gave us our next carboxylic acid. This acid was then coupled with an ester-bearing vinyl iodide to give California red scale pheromone alongside an undesired cyclized byproduct. This product was the result of a radical generation from the corresponding redox-active ester, followed by a rapid 5-exotrig cyclization before this radical was intercepted by the appropriate nickel-alkenyl complex. To overcome this problem, we simply increased the nickel loading, which in effect increased the nickel concentration to allow for more productive radical capture before an intermolecular radical cyclization could take place. Bringing the catalyst loading up to 40% and running the reaction more concentrated on a larger scale allowed us to shift the product distribution away from the undesired cyclized product to the desired linear product. In a final demonstration of the modular nature of our approach, we targeted the neuralidol series of olfactory terpenes. The neuralidols exist as 4 different isomers, 2 stereoisomers and 2 geometric isomers. Each one displays its own fragrant properties, and therefore there is value in having access to each as a single isomer. With our platform, we can access each isomer using stereo-defined alkene and carboxylic acid building blocks after TBSD protection of the tertiary allylic alcohols. While we have been able to obviate protecting groups in the past, the alcohol in the redox-active ester readily lactonizes if not protected. One particular neuralidol that I would like to highlight is the synthesis of RZ neuralidol. We returned to our ASIM Chem collaborators with these new conditions utilizing the silver nanoparticle functionalized electrodes, and they were able to translate that chemistry to a 100 gram scale flow reaction where we were able to generate decagram quantities of desired product. Further, SEM analysis on the carbon felt electrodes used in the flow cell revealed the presence of the same silver nanoparticles that we had utilized on small scale. To close, I would like to highlight the fact that this project was the direct result of key interdisciplinary collaborations. This project was born out of a total synthesis challenge in finding a way to access linear polyenes in a streamlined fashion, employing radical cross-coupling. Many of our hurdles were overcome by the invention of new methodology and exploring transition metal electrocatalysis, where we made the serendipitous discovery of our key silver nitrate additive. These findings were understood by interdisciplinary collaboration with the Anderson and Abrunja groups with expertise in surface microscopy and mechanistic electrochemistry, which helped us better understand our findings and stimulate our exploration of further synthetic applications. This project would not have been possible without our colleagues at ASIM Chem, University of Utah, and Cornell University. Teamwork makes the dream work. With that, I would like to thank my advisor Phil and my talented project partner Stephen Harwood, who was the true mastermind behind our synthetic approaches. I would also like to thank Professor Scott Anderson and Dr. Paulo Perez for their contributions in characterizing our electrode surfaces. Additionally, I would like to thank Professor Hector Abrunja and Kara Gannett for their expertise and insight in working to understand the explicit role that our silver nanoparticle functionalized electrodes were playing in our reaction, as well as Zhen Yao and Li Ji Sun for their help in scaling up this chemistry and flow. Finally, I would like to thank Matt for the opportunity to have me on the show. Thanks, Matt.
Thank you for joining us for this Research Spotlight episode, and thank you to Max for a really outstanding talk. If you enjoyed the episode, you can support us by subscribing and telling your peers about this podcast, and feel free to send us any questions or comments you have. Follow us on Twitter to stay up to date, and see you all next time.